Okay, we're going to be having a look at uh, three dimensions today, which give us volume and also capacity. We'll talk more about that a little bit later on, but let's have a look at how three dimensions ties into all the other diagrams we've seen so far. We've covered one dimension, length, for example. We've covered two dimensions, which is area. And today we're going to have a look specifically at three dimensions. And I've got a rectangular prism in front of us, and we can see the three dimensions there. We've got weight, length, and width in this rectangular prism, and that gives us three dimensions, hence the word or letters 3D. Okay, and 3D means that we can have a three-dimensional container, and in that container we can fill it with liquids, we can fill it with objects, and this container has a space. So when we talk about volume, we're talking about space, and we talk about capacity, we're talking about how much liquid we can put in that space. All right. Again, when we talk about three-dimensional formulas, they're all given to us in the exam. We don't have to memorize them. They get given to us in the question, which is a good thing. So you don't have to worry about the formulas, but I'm going to have a look at each shape and the formulas so you know which dimension to put in where in the formula. Let's have a look at these three basic shapes today. So we have the triangular prism, the rectangular prism, and then the one that's a little bit different is the cylinder. Okay, and you'll see here in all three of these shapes that to create three dimensions, all we need to do is take the base. Okay, so if we take the base of each shape here, we have this triangular base. And when you multiply that triangular base, which gives you area, and you multiply it by height, then you will find its volume. And if we take the rectangular prism, again, we have a rectangular base or a square base. And to get volume or three dimensions, we just need to multiply it by the height of that rectangular prism. And the same goes for the cylinder. It has a circular base, which gives us a circular area. And to find the volume of a cylinder, we just have to multiply again by height. So it's real easy to remember all 3D objects in math literacy. We have a 2D base, which is an area at the bottom, and then you multiply it by the height of the shape, and that will give you your three-dimensional volume. All right, so let's take the first one here. We have the triangular prism, and the variables we need to know here, if I write the formula out, we'll have a look at them. So to get volume for this triangular prism, we need to have half times base times perpendicular height, and I'll speak about that now. And then we need to multiply it by height. Okay, now this can be a little bit confusing because we've got two h's in our formula. All right, but that's nothing to worry about. I'll show you exactly which one is which. But when I write this formula out, I write this height with the perpendicular sign, and I'll show you where that is on the diagram. This height over here at the end is the height of the 3D shape, and I'll show you where that is as well on the diagram. So here in our diagram for the triangular prism, we have the triangle at the bottom, and the base of the triangle at the bottom is here, and that needs to have a perpendicular height coming off it. So the perpendicular height comes off our base, and it must come off at 90 degrees, as you know. And if we put our base and perpendicular height into this formula so far, this portion of the volume formula, I don't know if you can remember that, but that is the formula for the area of a triangle. Okay, so this part here is the area part that I spoke about earlier. So if I go back up to our shapes over here, the triangular prism area at the bottom here, okay, that is this portion of the formula here. Okay, so all we have to do is work out the area of the triangular base and then multiply it by the height. Now where is the height? That's this h on the side over here. Okay, so this h here is your perpendicular height, and that is this one in the formula over there. All right, so these two heights, the perpendicular height, which is on the triangle, and the height of the 3D object going up. Those are the two heights that we're talking about in the triangular prism formula. So just be careful when you see all the dimensions in your diagram, knowing which one to put where and which one is which. Just be careful of that. All right, let's have a look at the rectangular prism. This one is quite easy to do. So the formula for the volume of a rectangular prism is V equals, and then we're going to have a length, all right, times a breadth, or you can say width, and then we need to times by the height. Okay, so in our diagram, I'm going to say that this is my length, this is my breadth or width, and this dimension on the side here is going to be my height. Okay, so again, this height over here is this blue line on the left hand side there. All right, and again, this area of the shape at the bottom, square or rectangle, that area there, that's the formula for area of a rectangle. Okay, so all these volume formulas just take the area of the base shape and multiply by the height. Let's go on to the cylinder. Okay, so the volume of the cylinder needs a circular base. So we need the circle area formula. So that's pi times r squared times height. Okay, and you'll recognize this portion of the formula again. That's the area of a circle. So the base at the bottom of the shape is a circle, and then we just multiply by the height. So all we need for the circular area formula is r for radius. So we just get the radius from the diagram there. Sometimes they'll give you this dimension as a diameter. All right, so sometimes they'll draw a line across there, and they won't say that's radius. They'll say that is a diameter. So we'll put a D there for diameter. Well, you know, to get your radius, you just have to take your diameter and divide it by 2. Cut it in half. Okay, so don't worry if they give you a diameter in the question. You can take that diameter, cut it in half, and then that radius will be going into your formula. All right, now underneath here, I've shown you this funny symbol here. Again, we've seen it before in the previous lesson. That is a symbol for pi. Pi is just a number that always goes into circle formulas. So you don't have to remember it. They will usually give it to you. They usually say pi is equal to 3,142. It has no units. It's unitless. It's just a number. You just plug it into your formula straight over there at the pi symbol. Now, sometimes they'll say that pi is equal to 3,14. You just use whatever pi value they give you in the question, and you will substitute that straight into the formula. All right, and last but not least, our height of the cylinder, again, is on the side there. That h over there goes into your formula over there. So we see in all of these formulas that they're all made up of a base part, which is the shape of the base of the 3D object, and then you just multiply by the height of the object. Okay, now don't get confused, because sometimes these objects can lay on their side. All right, they can be on their side. So I'll try and draw an example of that over here. I'll try and draw a cylinder on its side. So you could have an object like this lying on its side. Okay, and they'll tell you that this dimension over here is the radius. Let me put it in red so you can see it properly. All right, so that little line there will be the radius, r, that you need for your formula. And now, because the object is lying on its side, this dimension over here, the height, is no longer going up. It's just going across over here. Okay, so that is still the height. Even though it's lying on its side, it doesn't look like a height. We still call it h, but it's just that the cylinder is lying on its side. Okay, so it's as if someone has knocked the cylinder over. It's still h for height. It doesn't look like a height, but it's still h, and that can still go into your formula over there. Okay, so these are the formulas we use. You don't have to remember them, like I said. You just have to know which one is which. All right, now I mentioned volume and capacity. So are these things different? No, they're not different. They're exactly the same. There is a slight difference. Volume is about space of inside a 3D object, and capacity is about how much liquid the 3D object can hold. So what they'll do is if they mention capacity, okay, if they talk about work or give the capacity, you just have to convert from your volume units into your capacity units, and I'll show you how we do that now. Okay, so the conversion, and just remember conversions have to be given to you. Okay, the conversion, except for the metric system, don't forget about that. So the conversion for volume to capacity is 1 centimeter cubed is the same as 1 milliliter. All right, and on the left we have volume. It's about how much space is inside a 3D object, and on the right we have capacity. Okay, so these two are interchangeable. If you get given an answer that's in centimeters cubed, the question might say, will you please change this into milliliters or liters? Well, we need a conversion to go from the one to the other, and we can use this conversion here on the screen, which is 1 centimeter cubed is equal to 1 milliliter. Now, they don't always give you this conversion. They might give you a different one. They might say, for example, they might say that, let me rub this out quickly. They might say 1,000 centimeters cubed is equal to 1 liter. All right, that's another conversion that they might give you. Whatever conversion they give you, you're going to use in the question to change from either volume to capacity or back again from capacity to volume. All right, so you will use the conversion they give you. They have to give it to you, and you can change between volume and capacity. All right, so let's have a look at a contextual question. Okay, now if I scroll down, you'll see this is quite a long question, but don't worry, don't stress. We'll take each little bit by bit, and we'll get through the whole thing. All right, so here is the context. There is a story here about a company that manufactures electrical geysers. Geysers are those machines that heat your water. And these geysers are made from steel in the following two shapes. Geyser 1, which is here on the left, which is a cylinder, and geyser 2, which is here on the right, which is a rectangular prism. Just remember, if they're going to ask you to calculate volume or capacity, they have to give you the formulas. Okay, so let's see what formulas they give us. But we have all the dimensions provided for us on these diagrams. One thing to check, very important, is what are the units they give us. Okay, so in the cylinder geyser, they give us meters for both of the dimensions. Okay, and for the rectangular prism, all the dimensions are in centimeters. Okay, so just remember that. They're giving us centimeters for the rectangular prism, they're giving us meters for the cylinder. And if I look at the rectangular prism, these are all centimeters, and we don't have millimeters and centimeters together in one diagram. They're all the same, which helps us a lot. Otherwise, you might have to change them all to the same units before you put them into your formula. So just look at your units and see what you're given. The question might be asking us for the same units, and we're just checking that they're all the same in the diagrams. Okay, here comes question 2.1.1. Calculate the volume of geyser 1, which is the cylinder over here on the left, and we need to work it out in meters cubed, which is fine because we have meters in our diagram. All right, and they give us the formula here. So the volume of the cylinder is equal to pi times radius squared times height. Okay, and again they ask us to use pi with this number as 3,14. Okay, so we will use the formula exactly like they give it, and we'll use pi just as they've given it to us. We'll just sub it into our formula. So V for volume is equal to pi. Now I'm going to start subbing the numbers in straight away. I've shown you the formulas. I'm going to start putting all these numbers in right now. And if we go to our diagram, we can see here that the radius is up there, and the radius is 0,4. It's not a diameter, it's a radius. So I say 0,4. Okay, and I'm going to write their meters, and I'm going to put a bracket around it. All right, and as I mentioned before in our previous lesson, do not think that the square is on the meters. Okay, what often happens is students, they'll write 0,4 and they'll write that, which is meters squared. Okay, now why is this a problem? Well, what often happens is students will write this down. They'll reach for their calculator. Maybe you're nervous or you're not thinking clearly. And then on the calculator, if I just pull the calculator up here, on the calculator, they will type in 0,4 and they'll look at the formula and say, oh, well, this isn't 0,4 squared. This is 0,4 square meters, which means that the 2 belongs to the m. All right, and they will disregard the square and they won't put it on the 0,4. Okay, so you've got to be very, very careful with that. The square belongs to the number 0,4. All right, so what I like to do is I like to put the whole thing in a bracket just to be safe. And then we also need to multiply by the height, and the height is here on the cylinder. It's 1,2 meters, so we're going to write that in there as 1,2 meters. Okay, now let's let the calculator do the work for us. So I'm going to say pi, the pi they gave us is 3.14 multiplied by, I'm going to use my brackets here, 0.4. Okay, the calculator doesn't take meters. Another reason that the square doesn't belong to the meter. All right, some people think that the 2 belongs to the m. No, it belongs to the 0,4. So I'm going to give that power of 2 to my 0,4, and then I'm going to times by 1,2. All right, and then get an answer. And we've got quite a few decimals here. Now, they don't tell us what to round off to in the question, so we always fall back onto the default, which is always 2 decimal places. So I'm going to look at the 0, which is the second decimal over here. Does the 2 next to it change it? No, it doesn't. So that's going to leave us with 0,6 meters squared. Okay, so these units here, this is not, the 2 doesn't belong to the 6 now, it belongs to the m. These are square meters. Okay, they gave us meters in the diagram, but sorry, my apologies, not square meters. We need to talk about cubic meters. Hey, this is volume. All right, so it's a 3. So volume is always in cubic meters. So our answers units will be in meters cubed. So those units there that I've highlighted in yellow are the units for the answer. It doesn't belong to the 0,6. All right, don't go into your calculator now and press 0,6 cubed. That 3, that power of 3, that cube belongs to the m for the units. Okay, so there's our answer for question 2.1.1. All right, now let's move on to 2.1.2. What are they asking us here? They say the volume of geyser 2 is 768,000 centimeters cubed. So they've done the calculation for us. They're telling us it is 768,000, and they say if 1,000 of those centimeters cubed is 1 liter, convert that volume into liters. All right, so they're giving us a volume, it's in centimeters cubed, but they want us to convert it into liters, and they're telling us every 1,000 centimeters cubed of that volume is 1 liter. So tell us what the volume is in liters. All right, so what we're going to do is we're going to take our volume number, and what we're actually doing is changing this to a capacity. All right, theoretically speaking, this is becoming a capacity. So we're taking this value here and we're dividing by 1,000 because we want to know how many thousands are there in this big number. So we're going to divide by 1,000. So it's 768,000 divided by 1,000, and that gives us 768. Okay, and we're converting here to liters. All right, so all we had to do was take the volume that they calculated and convert it into liters. Okay, easy enough. Well, yes, it's only 1 mark. All right, so now we're going to go to question 2.1.3. And they're saying if 1,000 centimeters cubed is 0,22 gallons. So now this is going from imperial on the left, metric on the left to imperial on the right. So they want us to do a metric to imperial conversion. And remember, for that, they always have to give us the conversion as well. So they've given it to us. They're saying if 1,000 centimeters cubed is 0,22 gallons, how many gallons can geyser 2 hold? All right. Now, where is this volume for geyser 2 going to come from? Well, we've seen it here already in the previous question. They gave us the volume of geyser 2. Geyser 2 is 768,000 centimeters cubed. So that's what we're going to refer to. They want to know how many gallons is that if you use this conversion. Okay, so every 1,000 centimeters cubed in our volume is going to be 0.22 gallons. So how many thousands do we have in our volume? We're going to do exactly the same calculation as before. We're going to divide by 1,000. Yeah, we know how many thousands are there in this number. And just like before, we're going to get 768. My apologies. 768. Okay, now I'm not going to write any units here. There are 768 thousands in this value. And they're telling us, well, every one of those 1,000 centimeters cubed is 0.22 gallons. So how many gallons do you have? Well, there are 768 of these 1,000, and each one of these 768 must represent 0.22 gallons. So I'm going to say there are 768 of these 0.22 gallons. So then in total, how many gallons do we have? We'll use the calculator for this. We'll say 768 times 0.22, and we'll get 168.96. That's already 2 decimal places. So 168.96, 168.96 gallons. And the gallon, the way you write it is GAL, gal. Okay, so that's how many gallons in our total volume over there. All right, let's move on to question 2.14. I'm just going to pull this down a little bit if I can. All right, 2.14. Okay, let's see what they say. To prevent loss of heat, geysers are covered with an insulation material pasted on all the outside surfaces. How many square meters? So yeah, this is what they want. They want square meters of insulation material will be needed to cover geyser 1. So we're referring to the cylinder here, okay, which is the one on the left. How many square meters of insulation material will be needed to cover geyser 1? Use this formula, surface area of a cylinder. So we want to know if you wrap this cylinder in insulation material, how much insulation material do you have? And you have to tell us in square meters. Now, surface area is the surface of this object, and not what you can put inside. It's all the area outside of the object. So if you had to wrap it in paper or something, how much paper, if you open that paper back up again, how much would you have? We're not using paper, we're going to use insulation material, and they're asking us to use the following formula. It's for surface area, okay? So I'm going to write the formula here. I'm going to say SA for surface area, and I'm going to fill in all these values over here. So we need pi, and they're telling us that we have to use pi as 3.14, so I'll put that in. Then we need an R, which is a radius, okay? So if we go back up to our cylinder, remember the radius was 0.4. And they want us to put in H, which is a height, and that is 1.2. So we have all our values. We just need to substitute them into this formula. Okay. So let's start filling it in. So we need 2 times pi, which is 3.14. This is going to be quite a long formula. Times R, which is 0.4, times the height, which is, I think it was 1.6. Let's check. Sorry, 1.2. Okay, 1.2 meters. All right, that's the one part of the formula. Let me move over a bit. Now we're going to do the other part of the formula. In fact, I'm going to put a bracket around here saying it's 2 parts. I'm going to do that one, and then I need to add it to this second part here, which is 2 times pi, which is 3.14. They gave us pi as 3.14 times the radius, which is 0.4, and that needs to be squared. And now you notice I haven't put any of my units in. So this is meters, and this is meters as well. Okay, so just checking we're all working in meters. Now you might think there's a lot of brackets everywhere. It's okay, the brackets are just telling me that I want to do certain parts of the calculation separately. Okay, so it's like putting compartments on all of this. Otherwise, what it would look like, let me rub out all the brackets. All right, it would look very long, and you might miss that there's a plus over here. Okay, so I'm just compartmentalizing my formula so that I know that there's different parts here. And then we can actually put this whole thing onto our calculator. There's a lot to type out. All right, I'm going to use brackets again. So I'm going to say 2 times 3.14 times 0.4 times 1.2. All right, that's the first part of the formula. And then the second part of the formula, we have 2 times 3.14 times, and now I'm going to say my radius, which is 0.4. This must be squared. Okay, so if we go back now to our formula, I'll just quickly breeze through it from the beginning. Okay, so we've got 2 times pi times the radius times the height, and then in the other part of the formula, let's say 2 times pi times the radius, which is 0.4 times the height. There we go. And then plus, I'm looking at the formula in the screen and my question. Yes, I've got that. I've got that. I've got that. Yo, it's very long. So I'm just checking that I've got everything in it. It looks good. Calculator does all the work for me, and it tells me I need to write down 4,0192, but I'm running off to 2 decimal places. They didn't tell me to run off to anything else, so always fall onto 2 decimal places. So I'm looking at the second decimal, and the 9 is definitely going to change this 1 to a 2. Okay, so 4,02, and they wanted this in meters squared. Because we used meters all along, we're fine. So we're going to say meters squared in our final answer, and that's it. So the hardest part was plugging in all the information into the equation. It's a very long equation. Please be very careful putting the right things in the right place. Okay, and here we have the final question. It's 2.1.5. What are they asking us here? They say a 1 liter tin of glue used to paste the insulation material can cover an area of 1,25 square meters. So a 1 liter tin covers that much area. Okay, so 1 liters covers this much area. Calculate the surface area that a 5 liter tin of glue can do. So if 1 liter can cover this area, how much area can a 5 liter tin do? Well, that's not too difficult. Now, can you notice that the previous question had a lot happening, but this question seems a lot easier? Well, the mark allocation is confirming that. So the previous question was 4 marks, and this question is only 2. So it makes sense that it's a little bit more simple to calculate. All right, so now we're going to say if 1 liter is 1,25 square meters, what area will 5 liters do? So if I have 5 of these cans, and each one covers 1,25 square meters, how much will that give me? All right, just remember this 2 doesn't belong to the number. That's part of the units. Okay, so it's 1,25 square meters. It's not 1,25 squared. All right, so it's 5 times 1.25, and that gives us 6,25. So this is how much area 5 cans will do if 1 can is just 1,25 meters squared. All right, I hope you guys enjoyed that. It was quite a long contextual question, but we covered it bit by bit using the knowledge about the volume formula. And just remember, they give us all the formula. They give us pi. You just have to know where to put everything. The only thing, no, in fact, they give us all the conversion formulas. They give us everything to do this. It's just a lot of substitution into these equations. All right, so just be careful when you're dealing with a long equation. Make sure you're putting in the right numbers in the right place. Check your units are all the same in the equation. That's also important, and you shouldn't have much of a problem. All right, guys, we'll see you next week.